Good afternoon, everybody, and welcome to our third press conference of this General Assembly. The European Geosciences Union is the largest European geoscience conference in Europe and the second largest in the world, where this year we have more than 20,000 people both on-site and virtually joining us. So today's press conference is a Juno mission briefing by NASA, and we have Scott Bolton from the Southwest Research Institute, Shannon Brown from Jet Propulsion Laboratory, Alessandro Mura from the National Institute of Astrophysics in Italy, and last but not least, we have Yochai Kasbi from the Weizmann Institute of Science in Israel. And now I'm going to hand the floor over to Scott Bolton.
Okay, thank you very much. So, let's see. You're going to start this slide? Yeah, okay. So we're here to present to you the latest results from the Juno mission. And you can see an image of our spacecraft. It's solar powered. There's 3 giant solar arrays. And this spacecraft cartwheels through space. So that's spinning twice per minute. And it makes all the observations that we're going to talk about in order to get our results. And so we're actually in orbit around Jupiter today. Next week, we will go by Jupiter. We go very close every 30 days or so. And next week will be the 72nd orbit. We arrived at Jupiter back in 2016. We launched in 2011. And so we've gone through 71 orbits to date. And next week will be the 72nd one. And so the results you're going to hear about today are a number of different topics. The first speaker will be Shannon, and he'll be talking about results of the moon Io, which is the most volcanic body in the solar system. And in particular, he's going to be talking about results from an instrument that we call the microwave radiometer, MWR for short. And this is an instrument that was invented in order to see through the cloud top. So you see these incredible clouds of Jupiter, and this instrument was designed in order to be able to see through those cloud tops down deep into the atmosphere and to understand the dynamics, and more importantly, the composition of Jupiter in order to help us understand how it formed and evolved. But he's going to be talking about the application of that instrument when you pointed it at Io. So over the course of Juno's lifetime, our orbit has slowly evolved. And during the prime mission, we avoided all the satellites, and we only went through and studied Jupiter. And we mapped it out. We made a lot of different kinds of science associated with understanding Jupiter, the body, and its magnetosphere. However, during the first extended mission, which started in 2021, the orbit had been moving and migrating naturally because of Jupiter's gravity field. Jupiter is oblate, which means that the middle of Jupiter is a little bit fatter than its poles, and that twists our orbit around. And that allowed us to eventually pass by the Galilean satellites, Ganymede, Europa, and Io. Shannon's going to talk about the application of this instrument that sees through the atmosphere, what it did when it looked at these satellites, and in particular Io. When we looked at Europa and Ganymede, we actually could see through some of the ice, and that was the first results of a resolved picture of what the subsurface ice looked like on Europa and Ganymede. When we pointed to Io, it wasn't so clear what we'd see because it's mostly rock, and we thought, well, maybe we won't see anything. But he's going to talk about results that surprised us. We saw actually into the lava a little bit. And what we can learn about Io from this instrument. The next speaker will be Alessandro, who is the lead scientist for our infrared camera that's built in Italy. And he's going to be staying on this topic of Io when we flew by close, but we also monitor Io from a distance, and we monitor this most volcanic body in the solar system and see all of its activities. And so he's going to be talking about what we've learned from this infrared instrument about how the volcanoes on Io work, how they're similar or different from that on the Earth. And then the next speaker is Yochai, who's going to go back to Jupiter and talk about the polar cyclones. So over the top of Jupiter, both poles are what we call polar cyclones. The south has one number, and they're all kind of arranged in a geometric pattern. This is one of these polar cyclones kind of close up. It's a very beautiful hurricane-like feature. He's going to be talking about how these hurricane-like features work, what makes them stable, how they move, what we've learned about the polar atmosphere of Jupiter, and also talk about the fact that as this orbit migrates that allowed us to go and see the satellites, Jupiter's been moving around the sun, and we now are going behind Jupiter. Our original mission stayed only up front where we're solar powered. We wanted to be pointing at the sun all the time and get data or get energy. And now we're actually passing behind Jupiter, and we get to do an experiment called occultations, where you can learn about the upper atmosphere. So he's going to explain how that works and what we hope to learn and what we've already learned a little bit from this. And then we'll close the comments where it'll come back to me, and I'll show some of the latest results from our images in the last orbit. And our images are kind of special in the sense that we take the raw data and we put them on a website, and actually the public make the pictures for us. We call it citizen science, and they are going to show you, or I will be able to show you, how we bridge really science and art, because you can see Jupiter is sort of half art, half science. So with that, I'll pass this on to Shannon, and you'll have to find that cursor again. I'm sorry.
There we go. All right, thanks, Scott. So, yeah, Shannon Brown from Jet Propulsion Laboratory. I've been involved with Juno for a little over 20 years, and probably one of the most exciting missions I've been involved with, because every time we orbit Jupiter, we learn something new, and recently learning a lot new about the moons, which I'm going to talk about here, and I'll share some exciting new results from the microwave radiometer. So this instrument, as Scott said, was designed to see uniquely down deep into the Jupiter's atmosphere, hundreds of kilometers deep. We do this using 6 different wavelengths, ranging from 1 centimeter to 50 centimeters, so very short to very long. And that longest frequency allows us to see very deep, hundreds of kilometers into the Jupiter's atmosphere. And to do this, we need very specialized instrumentation, particularly to survive in Jupiter's environment. Not only that, because we're measuring at a long wavelength, the antenna has to be huge. It actually drove the size of the spacecraft and was about as big as we could fit into the rocket. And you're seeing a picture of, or actually a video of that here. You can see standing next to the antenna engineers. It's a pretty large antenna compared to them. Not only that, it probably looks a little unique if you're used to thinking about like microwave systems, like say a satellite TV dish. An all-metal design, and the reason for that is we started out with a more traditional design for the antenna, but we realized that as it was going to be circling Jupiter, it was going to build up charge and start sparking, and that's certainly not something that you would want to have happen to your instrument as you're going around. So the engineers came up with this really unique design that was specially designed for the Juno mission that has been operating very successfully in the 9 years that we've been orbiting Jupiter. So what we've been able to do, so most of our early mission observations where the orbit was much closer to the equator focused on understanding the deep atmosphere at the equator, temperature and the composition. But as the extended mission progressed and the orbit moved closer to the poles, we've been able to really take the microwave instrument and look more closely at these very dynamic storm features that are circling the North Pole. And you'll hear a little bit more about them at the end of the briefing from Yohai. These are big circumpolar cyclones. It's very similar to hurricanes here on Earth, except they're much larger. They're about the size of Australia. And they circle the North Pole very slowly. And now we're finally able to resolve them with our microwave instrument. So before we knew about how big they were in horizontal extent, but now we can see just how big they are in vertical extent, how deep they go. And it turns out they're not only big horizontally, they're huge vertically, about 10 times the size of hurricanes that we have here on Earth. The microwave instrument, it's not shown here, but also is showing us where the lightning is happening around these. It's happening around the edges of the storms, similar to the way it happens on hurricanes here on Earth. And pretty much, you wouldn't, if you were on Jupiter, you wouldn't want to be anywhere near these storms. But what the results I really want to show with you is when we took this instrument, which was designed to uniquely look deep into the atmosphere and were able to look at the moons because the extended mission flew by very close by Ganymede, Europa, and Io. We've been able to then see into these bodies, these icy or rocky bodies that we had never really been able to look into before. This is the first time we've been able to see into the subsurface of these bodies. And the power of Juno is we have multiple wavelengths, multiple instruments that can look at these bodies. So what you're looking at here are three different wavelengths from the visible on the far left side. That's what our eyes see. So you're seeing colors, topography, very high resolution imagery. In the middle, you're seeing infrared. And Alessandro's going to talk more about the infrared. That's showing us where all the surface heat is distributed. And then the last image on the right, that's the microwave image. So this is the first time that we've been able to see the subsurface temperature. So not just these surface features, but into the subsurface. It's kind of interesting what this has shown us. So if you ask really anyone on the Juno project, maybe with the exception of Scott, we didn't think that we were going to see anything all that interesting with the microwave radiometer looking at Io, because we're seeing maybe 6 to 10 meters into the subsurface. If you compare that to the entire lithosphere, the crust of Io, which is about 35 kilometers or so, it's a very small fraction that we're seeing into the subsurface. So we didn't really expect to see much of a temperature difference between the shortest wavelength, which is seen very close to the surface, and the longest wavelength, which is seen about 10 meters down into the surface. But when we looked at the data, it really surprised us. Io surprised us. What we saw was a very significant frequency dependence in that the shortest wavelengths were seeing a cold temperature, whereas the longest wavelengths were seeing a very high temperature and much increased temperature. And the way that we can explain this is if you have subsurface or near surface heating, so like, for example, a lava flow, that long wavelength observation is going to be able to punch through a crust that often forms on lava flows and see that hot magma, where the shorter wavelengths are going to see that cold crust. And just like the infrared would only see the surface, the short wavelengths of MWR would just also see that surface. So this, for the first time, is saying that there is a significant portion of Io's surface that is potentially covered with these near-surface active lava flows. And we've never been able to see that before. And it's extensive. It's everywhere we looked. It wasn't just one or two places. Everywhere we looked, we saw this increased surface heat, which could be in the form of lava flows where you develop an insulating crust, just like here on Earth. And it was about 10 to 15% of the area of Io, which is about a little over half the size of Europe. So that's a lot of extent. And then the other thing that we've been able to infer from the microwave data is the surface is very low density, very similar to like a volcanic pumice rock here on Earth that forms when magma cools and gases evaporate and expands like a sponge, and it's less dense than water. You can see an example of that floating in water. So we're not saying that it's exactly pumice, but it just appears to be a low density material like perhaps dust or a very low density rock. So this is very unique. We've never been able to see into the subsurface of any of the moons before, and this is the first time that we're looking beneath the surface of Io. So now I'm going to pass it on to Alessandro, who's going to continue the discussion of Io and tell you more about what the infrared observations are telling us.
Thank you, Shannon. Alessandro Mura from the Italian Astrophysical Institute, and now I'll talk you a little bit more about the volcanic moon of Jupiter, Io. So as Scott told you, Io is the most volcanic object in the solar system, not only for the amount of volcanic centers, but also for the energy they release. And in this movie, you're seeing the interior of Io as we think it is after the observation that Juno did in 2024. So the interior of Io, according to our observations, is completely filled by magma chambers. They are scattered all over around, more or less the same way that a sponge is filled by holes. And these magma chambers are energized because of the enormous tidal interaction with Jupiter. So being Jupiter so big and Io so close to Jupiter, basically the Jupiter deforms Io, it squeezes it. And this energy has to go somewhere, and it goes to the surface where eruptions occur. Okay, so during orbit 68 of Juno, the GRAM instrument, the infrared GRAM instrument on board Juno, had the chance to measure, to observe something really unexpected. It is the largest eruption ever recorded on Io, that probably matches the largest eruption ever recorded on the Earth. Right, so now you're seeing a movie of this eruption. Of course, the eruption is the big spot in the center of the movie. Okay, so you have to remember this is infrared light. So as Shannon told you, infrared is very good because it's not visible to our eyes, but it gives you the amount of energy, the amount of heat that the body is releasing. So it's very useful for this purpose because it's able to tell you the energy budget of something. Okay, so thanks to this data, we were able to measure the energy, total energy and total power of this eruption. Before going to the data analysis, I'm showing here a superimposition of images. On the background, you have the visible. On top, you have the infrared data. So the volcanic centers that we call hot spots are those bright spots over there. And you see actually Juno measured about 200 hot spots. So they are scattered all over around. In particular, now we are going to show you the observation of the South Pole, where before this observation, nothing special were observed. And now I'm showing you a movie of 4 months of observation of this region. Okay, so you're seeing the South Pole of Io, and you see nothing at the beginning, and then all of a sudden here the eruption, and then you will see the recovery after a few weeks. Okay, so thanks to this data, we were able to measure the total energy and total power of this eruption, which was huge. It was 300 terawatts. I would like to give you some context. 300 terawatts for several weeks is the same amount of energy that the total human civilization uses for 1 year. Okay, if you want to compare this energy and power with a volcano, so this matches very well, for example, with Mount Tambora eruption in 200 years ago, the age of Napoleon, basically. So what is this telling us? It's telling us that what is occurring every hundreds of years on the Earth, so it's very rare, on Io occurs very often because the previous record for an eruption was set on Io only 20 years ago. Okay, now this is the new record. What is even more surprising is that we observed that at the same time, many eruptive centers, many volcanoes, what we call patera actually, were erupting simultaneously with the central one. So actually, this region that was interested by this simultaneous eruption was very huge, the same size of France, 500,000 square kilometers. It's just like if France is filled by volcanoes and all of them are erupting all together, which is surprising because they need a system to communicate each other. So what we learned from this, we learned that the subsurface of Io, the immediate subsurface, should be filled by magma chambers, which are interconnected by magma channels or tunnels or pipes, whatever, so that they can talk each other and they share information about pressure changes immediately. In a few weeks, actually in 1 week only, actually, Juno will observe again this eruption, so we will be able to tell you more about the evolution of this giant eruption. And with this, I leave the ball to Yoai, who will talk to you about the cyclones on Jupiter.
Hi everybody. Going back to Jupiter, I'm Yochai Caspi from the Weizmann Institute of Science in Israel. I've been a member of the science team of Juno for the past 17 years, working mostly on gravity and atmospheric science. And today I'll talk to you about some very exciting atmospheric science results that we've been getting for the past months in the extended mission. And the reason that we can get this new and exciting result is the fact that Juno, for the past 18 months, has gone into this unique orbit where every time we go around the planet, we pass behind the planet from the point of view of an observer on Earth. So for an observer on Earth, if you want, Juno basically sets and rises behind the planet every time. And this orbit gives us the opportunity to do radio occultations, which you can see animated here, which is basically an experiment where we send a radio beam from the spacecraft to Earth. And as it goes, as the spacecraft sets and rises behind the planet, for an instance, this radio beam goes through the atmosphere, as you can see it here, grazing it here. When the radio beam goes into the more dense medium, then the radio beam gets bent. And what we do is measure this bending of the beam and interpolate that to understand the density and temperature structure of the atmosphere at every one of the points where this is happening. This experiment was actually done in the past by Voyager and Pioneer back in the 70s, but since then, for over 40 years, this was never done for Jupiter. And with Juno, we have much more orbits and opportunities to do this than before. In the 70s, we had 6 such measurements, and now with Juno, we already done 26. So we have 26 profiles, and we continue doing this every orbit, every time the spacecraft sets and rises around the planet. And what's special about this, this experiment is that this is an experiment that basically happens over 800 million kilometers. We're not only sending the beam from the spacecraft, but then we need to monitor it from Earth. So, and then see how it changes. So we're measuring these tiny little changes in the bending, which is of course exaggerated here, and changes in the frequency of the beam, and then we can interpolate this to get these temperature profiles of the atmosphere. Now, just as an example to the kind of things that we've been able to detect, I'm showing you here an infrared image of Jupiter as seen from Earth. So this is from the Vizier instrument, and you see at the cap of Jupiter this kind of darker orange region, which you can see here. This image was done by Lee Fletcher from the University of in the UK, from Leicester. Yeah, and the Vizier, as I said, is a ground-based instrument. And then I'm circling there in purple this polar cap, which we've seen from a long time ago, but really didn't know what it is. We knew it's colder, we knew it's in the stratosphere, but we had no other information about it. And with these radio occultations, just in the past 6 months, we had 8 opportunities where we probed through the polar cap and a little bit just to the south of it. I'm showing you here 2 examples of profiles that we retrieved here in blue within the polar cap and in red just south of the polar cap. And you can see that indeed the one inside the polar cap is colder by about 5 to 7 degrees, going all the way from about 50 kilometers above the cloud level all the way up to 140 kilometers. So this is the stratosphere of Jupiter. And with this, we could not only identify and kind of confirm that this is a colder region and by how much, but we could also use these temperature profiles to deduce the winds around this. So we know now that the winds surrounding this polar cap are about 170 kilometers per hour, just like over 100 miles per hour. Very, very strong jet streams surrounding this polar cap. This is similar to the stratospheric vortex that we have on Earth in its essential physics. But like anything else, but on Jupiter, it's much bigger and grander, and the winds are much stronger than we have on Earth. It's also more persistent. The Earth one varies with season, while on Jupiter, this is a persistent feature that exists all the time. Now, this all exists high above in the stratosphere. Now, if we dive down below and we go down to the cloud layer, then we can see these circumpolar cyclones that Shannon mentioned before. And we have 8 such cyclones surrounding the polar cyclone in the north and 5 such features in the south. And these are really unique features that we see only on Jupiter. It's the only planet in the solar system where we have these circumpolar cyclones. And the image that you see here is an image from GRAM, the same instrument that Alessandro just talked about. So you're looking here at infrared, and brighter is warmer and darker is colder. And what's new here is that since we've been tracking these features for almost 9 years now, since the arrival of Juno Jupiter in 2016, then we're getting more and more information about the movement of these things. We see them kind of drift around over these 9 years, and they also bounce around each other. And with tracking them over time, we've now been able to understand the physics of what's holding these cyclones together and why are they there from the first place. As mentioned before, in essence, these are just like hurricanes on Earth. These are cyclones. They rotate in a cyclonic fashion. They're fueled from below, from the heat. But different than hurricanes on Earth, which exist in low latitudes and are kind of singular features. We never see a few of them clustered together. On Jupiter, they all cluster together. Now, like hurricanes on Earth, cyclones have a tendency to drift towards the pole. In the Jupiter case, they all drift and converge towards the pole until they basically bump into one another. If I kind of zoom in on the polar cyclone, you can see it kind of slowly circulating around, and you can see how compact the system is, how the cyclones are really trying to push against it and get to the pole because of this tendency of cyclones to get to the pole, which is called a beta drift. That's a meteorological term. But then when they get too close, they feel the other cyclones and they just can't get close together. The way to think about this in a simple way is to think about this as a system of springs, which is animated here. So again, they have this beta drift, which pulls them towards the pole, but they can't get too close because of the existence of the other cyclones, and then they kind of basically bounce together. They bounce in a sense that they have a 12-month oscillation, so they drift constantly westward and also oscillate around themselves. And what we've been able to do now is by monitoring these motions over these 72 orbits of Juno, we can really track the physics, explain how these work, and then explains not only cyclones on Jupiter, but actually cyclones on general, a phenomenon that we don't have on Earth. So on Earth, because of their isolation, it's hard to learn about interaction between hurricanes or cyclones. On Jupiter, we've been able to do this. I'll finish by showing, I guess that movie didn't come up here. But anyway, I'll pass it on now to.
The end of mine.
Yeah, okay, I'll pass it on to Scott.
Yeah, so the polar cyclones are really amazing at Jupiter, and they've stayed stable all this time. You know, we discovered them right when we first got there in 2016, and there were 8. And sometimes you see a new one coming in, but then it gets pushed out by the time we go around again, it's gone. So it's a very exclusive club. They don't like to let new members in. They're kind of very picky about that. So I'm going to show some images that we get from the Juno cam. So one of the things that's special for us, our camera, visible light camera, is really for education and outreach and public. And so it's called Juno cam. Here you're looking at maybe the most recent photos that we did of Io. These are not when we're very, very close, like when Shannon took the images, or even as close as where Alessandro showed some things. But these are about 85,000 kilometers away, but still you see a lot of features, and this is a really good resolution, and we really can't monitor this moon or the volcanic activity from Earth as well as we can from Juno. So we've been able to do this, and that's one of the things that and so when Alessandro is able to see this in the infrared, this is what we're seeing in the visible, and you saw that one image where we mixed the two together. So these are made by a contributor to our website named Brian Swift, who's been able to analyze these and create these images for us. The next image I want to show is, so Yochai mentioned the idea that these days, now we go behind Jupiter, right? And that allows us to do the occultation, but we're also in the dark. And so Juno cam in the dark actually can look at the aurora. Now we can't see the visible light aurora from the Earth because it's lit up by the sun, and so we have to be in the dark, and we never see the Jupiter dark side, obviously, because we're on the same side as the sun. So Juno cam, this is the first time we went behind and they actually captured a piece of the aurora. So you see a photo of that on the left. On the right, you see sort of a map, theoretically, of what the auroral oval on Jupiter is like. The green kind of outlines it, and you see in the little arrow where we're looking with this aurora. And this is the first time we were able to see this on the 69th orbit. So it was relatively recent, and it was made by a person that contributes a lot to our science, Gerald Eichsteck from Germany, who went in and made this image for us. The aurora on Jupiter are the most powerful in the solar system, has the strongest magnetic field. And this is, just another example, as Yochai was saying, Jupiter's sort of an extreme planet. Everything about it is monstrous, and the aurora are no different. They're the meanest that we know of. So here's another image. On the left side, you see an image. This is in more natural color. This is how you would see it with your eyes if you were on a chair flying through space with Juno. And you can see the almost like the Van Gogh-like paintings that you see on this. And it's made by a contributor named Bjorn Johnson. On the right, you see where this has been, where he's taken it and exaggerated the colors a bit. It becomes a little bit more artistic, but at the same time, this is actually really important for us scientifically because it brings out the contrast so that we can see the different levels of the atmosphere. So these different colors are representing changes in the composition of that atmosphere or where you're seeing to different depths. And so you're really seeing how the dynamics of Jupiter works by through this true versus enhanced color. So it's both an artistic tool, but it's also a very important scientific tool. Here you see a very extreme case of that where Jackie Brink has actually stretched the colors even more. You saw this image earlier today, but where you're really looking at are these zones and belts. So when we all grew up, or even today, if you look at what you think Jupiter looks like, you see the zones and belts, these stripes going across the planet. You see a great red spot sort of in the south. It's a giant cyclone. And of course, Juno is going polar, so you see the poles and you see a different view than we've grown up with. The brown is really, these are the belts, and the wind is going in one direction, and the white is the zones, and the wind is actually going in the other direction. So this is like the Earth where you have these jet streams going back and forth that are creating a lot of dynamics. Here you see another storm. This is by a contributor named Kevin Gill, who's actually an engineer, but he's really good at processing images. And you can see this northern storm. This storm is sometimes called, I think, the little red spot. And it was discovered a few years ago, or quite a few years ago, but it's pretty amazing. And it's about 7,000 kilometers across. So you're looking at about half the size of the Earth for this storm. This is not the Great Red Spot, which is even bigger, but this is not far off of what those polar cyclones are. It's a little bit bigger. So this is an amazing storm unto itself. And if in the next slide, you'll see the same image. This is the image that Kevin worked from. Another person named Thomas Thermopoulos, who is incredibly good at making images for us as well, took an image that Gerald originally made and then processed it a little bit further, adding more colors, stretching it, recalibrating it. And you can see the same storm in the middle in more of an extreme color. And you can see how it is in the context. JunoCam is very special in the sense that its framing is very similar to your smartphone. So most cameras that go on spacecraft have very high res. They're like telescopes, and they can see really great detail, but small patches of sky. Juno's camera is much broader in context, like you would want for your vacations. Turns out it's really handy for science because you can see the context of this storm with the other storms all at once in an instant. And you can see the processing that is offered there. And then finally, I'm just showing you one. This is really, I think, maybe more art than science. Navaneeth Krishnan is also an incredible artist making images for us. This is a northern polar cyclone or hurricane. And you see when you get close up, it's not just a splotch, it's really a beautiful swirling hurricane. And so just like Earth, a lot of our atmospheric features, if we can see them from space, are incredibly beautiful. Jupiter's like that as well. And I think that might be the last slide. So thank you very much.
Thank you also very much for this very insightful presentation. So I'm going to open the floor now, both for our on-site and our online journalists and media professionals. So we do already have a question online, and it is a question for Dr. Mura. Apart from what you mentioned about density, what else have you learned about the composition of Io?
Okay, so to be more specific, what is interesting is the distribution of magma in the interior of Io. So there were different theories before the observation of Juno. For example, one theory involved having a global magma ocean, another having a more deep magma ocean or partially molten part of the subcrust or crust and mantle. Now that we have the observation by Juno, which were made by gravity measurements, so basically the same technique that Yohai explained to you, now we know that basically there is no actually global magma ocean, but rather this a range of magma chambers which are scattered all around. The question was also, are those magma chambers connected? Okay, so yes, this is actually the new result we are able to tell. About composition, that is difficult because we don't have an instrument which is able to give us the composition directly on the interior. We can tell that from the composition of magma that is coming out. But for the composition, well, from the structure, now we know that these magma chambers are connected, as I told you, and this should be a general. We think, and we will study in the future, whether this is a general behavior or only for the South Pole.
Thank you so much. Do we have any on-site questions?
Hi, thank you for that. Can I ask about the volcanic eruption, just to make sure I understand the context? So I'm right in thinking this is the biggest eruption ever observed, sort of beyond the Earth, and is it also is it the biggest that we've actually sort of seen in real time ever?
So basically, for Io, that's for sure the biggest eruption we ever recorded. Okay. At the Earth, of course, the comparison is more difficult, is risky, because at the Earth we have, for example, in terms of energy, at the Earth we not only have the measurement of the radiant energy, we also have the gravitational energy, the amount of mass which is released. It's something that on Io we don't have. So when I'm saying this compares to Montanbora or Krakatoa eruptions, which were huge eruptions at the Earth, I'm just saying that more or less it's the same amount of energy and power. But this is very remarkable because on Io, those gigantic eruptions, they are quite more often. In some way, this is not surprising because, as I said, Io is the most volcanic object in the solar system. So it surpasses the Earth because of the contemporary, at the same time, active volcanoes. So the Earth have more volcanoes than Io, but most of them, they're not active at the same time. On Io, all of them, they are continuously erupting altogether.
Thank you. I can also ask how do your findings relate to the sort of shallow magma? So you've got these magma chambers. Are they connected to these lava flows you've seen on the surface?
Well, actually, okay. So the result that there was no global magma ocean, which was much more deeper than what Shannon was mentioning, so it was something much deeper, was a result from gravity observation during the passages of Juno very close to Io during orbits 76 and 78, I think. 50, sorry, 57 and 58. Right. So that was a measurement, a gravity measurement. It's the same technique that Yohai told you. That is the perturbation of the spacecraft orbit due to the gravity of Io. And that is the result regarding the interior of Io, how we think it is structured. Now we add in more context because we have this theory about the connected magma chambers. Okay. So am I answering your question?
Not quite.
Not quite. So
how those magma chambers relate to the very shallow sort of subsurface?
So let me add a
okay.
for it,
Yeah.
for that. So, and Shannon can add to this on top of it. So the magma chambers, I mean, we found that there was no global magma ocean, which was a big puzzle and a big question, right? What's driving these volcanoes? Because they're all over the place. So many scientists thought there must be a global ocean. Plus, there's a lot of study of global magma oceans in early solar systems. We think they played a role at the Earth and the Moon and things like that. So when we didn't find this, we saw there was, we kind of solved this question. We thought, okay, they're individually made. Individual chambers are being erupted. With the discovery of this largest eruption being connected to multiple chambers, you have one reservoir maybe feeding multiple vents, right? So you've got something in between a global ocean and maybe something with, reservoirs that are sizable, but not all over the entire globe. So that's feeding this. Now, on top of those things, you get these formations like we see on the Earth, we think, of magma lakes And so Alessandro's made a lot of progress looking at things like Loki, which has this big, reservoir that kind of sits almost like in Hawaii, you see this big magma lake. So I think part of Shannon's ideas, when we try to understand, overall, how can we see this hot field going up, is that there's some percentage of Io's crust that has this magma lake-like reservoir underneath it, relatively shallow, not necessarily all the way down where you would see the eruptions, but it's still there. Just like if we went to Hawaii or some of Iceland, if you were brave enough to walk out on the crust and you weren't unfortunate to fall through or crack open, where you would, of course, perish. But right underneath that crust must be very hot stuff, right? And that's why if you go to Hawaii National Park, you're not allowed to go walk around those things, right? And so what he's seeing is evidence that he's seeing into that. And when he compares it to the infrared maps, he gets a rough idea of what's the percentage of Io that's covered with these lakes, because it's not everything. He can now take it a little further than what I'm saying, maybe.
Yeah, no, that's exactly right. Is the infrared tells us where the most active heat sources are, where things are coming to the surface. And up until recently, until we looked at Io with the microwave radiometer, that's all we've been able to see. And there's this other portion of the heat that's getting out of Io, which is would be invisible to these other instruments, the visible and the infrared. And that the new observation from the microwave is able to punch through those cooler insulating crusts and see that other missing heat, which will eventually help us close like the global heat flow budget.
If I can ask one more question about the aurora. So am I right, first of all, in thinking we have seen auroras on other planets like Mars, or am I wrong about that? And secondly, that picture is obviously just black and white. What do we know? Would it have colors if you could see it in sort of real visible light?
So the visible light is visible, but it's a mixture of color, as you point out. We see aurora on Earth has very strong aurora. We see it on Jupiter. Saturn has aurora. Uranus and Neptune have aurora. So you see it. Even Ganymede, the moon, which has its own magnetic field, may have some aurora. What's unique here is that normally when you look from the Earth, you can't see visible light aurora because you're looking at the day side, which is already washing out that aurora signature that's invisible. So we often use and see it in infrared or ultraviolet. Okay, so there is a spectrum there, and that spectrum is tied to, just like it is on the Earth, the color of the aurora tells you something about the kind of particles that are precipitating and what they're hitting, what kind of atmosphere they're hitting, and because they have to make emission, and that coupled to the energy in the molecule or the atom that's being energized. So the visible tells us something, and we can't really see it. And this is relatively new. There's, visible aurora has only been seen a couple of times. Galileo was able to see it, the spacecraft, Galileo, many years ago. And this is really the next time that we've been able to take a look at it. We will be able to see it not only from Juno Cam, but we have another camera on board that is a star camera, and the person that leads that is sitting behind you. She also will be able to see the aurora, and has already, with what's called the stellar reference unit, which is a very low light camera. So when you combine these different visible lights and you start to look at it, you can learn quite a bit about what is making the aurora, and in particular, what Heidi Becker with the SRU has been able to do is look on the side, and actually we will be able to see the altitude profile of this aurora, which has really not been done, and that's going to tell us a lot about the atmosphere. So we've just started to make those, but as the orbit keeps going, we're going to see that better and better, and that's a kind of a magical thing.
Thank you.
So, what do you have a question?
Hi, I just wanted to ask, when was measured the eruption on Io?
December 2024. End of December, 27th of December to be precise.
Okay.
So actually on Juno, we have the chance to observe Io every 2 months, so every 2 orbits. So we observed that in October, nothing. In December, giant eruption. In February, the recovery of the eruption.
Okay, thanks.
I did want to just follow up your question about the Shannon's observation with the MWR. So when we saw the heat, which meant we were seeing into it, that was really a surprise, right? That was the first time anybody's ever done that. So we sort of invented this instrument for Juno. As we said, it was really designed for the atmosphere, right? And the concept of radiometers is quite old. Radio antennas, we've used them a lot for many, many years. What was unique about Juno's was we combined many wavelengths, and we also changed the way it worked a little bit, as he started to describe. So it is a unique kind of instrument. When we saw IO and we could see into the lava, we realized that we've never done that for any volcanic on the Earth. And so now we're looking at, we may have stumbled into another tool that is going to be very useful for us to understand our own planet. And what was amazing is we stumbled into that by looking at a small moon 500 million miles away that was unbelievably volcanic. And then we had an instrument that was designed for the atmosphere of Jupiter, and then said, okay, so a lot of science gain or advancement sometimes is serendipity. And this was just another example. We can say, we planned this, but the truth is we stumbled into it, and we're going to make use of it. I'm guessing in the coming years, we will create instruments like this to try to learn about ourselves now.
Perfect. Thank you so much. Does anybody else on site have a question? Okay, so I'm going to conclude with a question of mine to Yohai. And I'm not an expert in the field. This is very new to me. But what causes the bending of the radio beam?
The bending.
Yes.
Yeah, that's a good point. So when you send the radio beam in vacuum, then it just goes in a straight line from the spacecraft to Earth. As the spacecraft is going behind the planet, then the radio beam begins to go into a medium which is denser. Okay, just like you put light into this glass of water, then as the light goes into the water, it bends a little bit. So when you're going into this denser medium, which is the atmosphere, the denser it is, the more the beam bends more. So as you go denser and denser, you get more and more bending. Of course, at some point, once you go behind the planet, then nothing passes through the planet. So we can just get the atmosphere down to just about to the cloud level. But we're getting it from hundreds of kilometers above to the cloud level every time we go around.
Thank you so much. I appreciate it.
You can see that effect yourself every day if you look at a sunrise and a sunset. And one of the reasons that they're incredibly beautiful and colorful, right, is that sunlight is being bent and changed by our own atmosphere. And so Yohai's using that trick.
Yeah, which here that is basically these different colors, right? The fact that you're getting different frequencies when the sunset, the later it is, you get more bending, meaning more redder colors, and that's these beautiful sunsets that Scott's referring to.
This technique is also used every day at Earth with GPS satellites that are continually going around the Earth, and we use those for weather forecasting on Earth. It was pioneered in planetary science, but now applied to Earth weather forecasting.
And one last question. You mentioned the artistic bit of this research. Are you working or collaborating with any artists that would present this as a science communication way?
We do. We collaborate with quite a few artists, not necessarily on image processing, although those are artists. Those are volunteers that basically go to our website. The data is open to anybody. We post it immediately. With some directions, and they process them. Some of them are artists, some of them are scientists, some of them are engineers, some of them are students in grade school that are making the pictures. And then when they make the picture, they can put their name and credits on it and send it to us, and we'll post it. Sometimes an artist will then take that and do something more with it. And there's been museum shows that we've helped with, but we also collaborate with sculpture type artists and musicians. So we have a large program where we mix with a lot of different artists that are inspired by space science.
And the musicians would do soundscape studies related?
I'm sorry?
And would the musicians do something related to soundscape studies or?
Sometimes, or they'll use some of the sounds or data that we have from Juno in their music compositions, or they will use them in their concerts in order to portray. So we've had things that I've worked on where we had displays, we helped with Coachella, that's, and a number of different South by Southwest, all these different festivals. And we had a collaboration that started back in 2016 or so with Apple Music, where we worked with many different kinds of artists, everything from rap to country to classical to hard rock, And so you can find many artists that have used this. Sometimes they're in concerts, sometimes they're just blended in, or we've, redone like Elton John's Rocket Man, where the percussion were actually plasma wave data from Jupiter that we folded in as a beat and rhythm. So there's the different artists have done that. That was a group named Little Big Town, a country music band from the US.
Thank you so much. Okay, one last call for questions. Yeah.
About the aurora, I'm also going to ask when the Juno cam did the images of the aurora.
Juno cam images of Aurora made. Just, I think, the last orbit. I'm not positive I know the exact date. We can get that for you.
70 maybe.
Okay, like maybe just the moon.
Just 70.
It was like,
February.
the 70th orbit. So we just went through the 71st orbit. So it was 2 orbits ago. So that's about
2 months ago.
60 days, not quite.
Okay. Thanks.
Perfect. Any other questions? Okay, well, now we are going to conclude our press conference. So thank you so very much for our speakers, for your time, and for all the information that you shared with us today. So let's give them all a round of applause. And I just want to say that tomorrow we are going to move on to our next press conference. It's taking time at 10 a.m. Berlin time, and it's titled Power Tripped, Building for the Future with Resilient Climate Technologies. So make sure to tune in. Thank you so very much.